Okay, let's continue our discussion on genome assembly algorithms. Today we will look at multiplex de Bruijn graphs and overlap graph based methods for genome assembly. So as a quick recap, in the last lecture we were looking at de Bruijn graphs and how do we use de Bruijn graphs for genome assembly. So in the last lecture we defined what de Bruijn graphs are. So just to remind you quickly that again you have a reference genome which is not known. You have the sequencing reads that are sampled from the genome. Now from these reads the de Bruijn graph is constructed as following. So the vertices of this graph are k-mers, that is the k length substrings observed in the sequencing reads. So all the k-mers observed in the sequencing reads are vertices in the graph, and you draw an edge between two k-mers if they share a k-1 suffix prefix overlap. So if you consider k-1 suffix prefix overlap and between these k-mers, then you will get a de Bruijn graph like this. So I am illustrating this de Bruijn graph method using a simple example, and we gave a formal definition for de Bruijn graphs, and then we went into significant details on how we can use de Bruijn graphs for solving the genome assembly problem. Now moving on, in this lecture I want to look at two other common methods for genome assembly, that is multiplex de Bruijn graph and overlap graphs. After I discuss these two, I will close this lecture by also looking at the role of sequencing technologies for genome assembly problem. So moving to the first point, let us start discussing the multiplex de Bruijn graph method. Now remember that a key parameter in building de Bruijn graph is parameter k, because k is what determines your length of the vertices, and k also determines what suffix prefix overlap length you are going to be using for drawing the edges in de Bruijn graph. Now you can ask, okay, what k-mer size should I use, because that is obviously going to change the graph topology, right. So for example, if I consider this simple example where you have a single read A G T G G T C. So for this single read, so you have a single read here. Now I can use k equals 2, I can use k equals 3, k equals to 4 and so on, and there is no particular optimal value of k that I can say that okay, this go with this value of k for solving the genome assembly problem. So there is no such optimal value that we have discussed so far. So this is the k-mer value is typically decided based on heuristics. So if you consider a small value of k, that is k equals to 2, you observe that your vertices are of length 2. So all these vertices are 2-mers, and you draw an edge when you observe a suffix prefix match of length 1. Now in this case the graph looks very dense, that is you do not see a chain like structure where you can easily spell the sequence from left to right. So this graph is very much tangled and there is no clear path that we should choose for spelling the read sequence. If you further increase k by 1, that is if you use k equals to 3, then the graph topology simplifies, but still we do not see a simple chain like topology where we can easily spell the read sequence. If we use k equals to 4, then this time observe that you have a much simpler graph topology in which you can observe or you can spell the underlying sequence from left to right. That is, I can start spelling the sequence from the leftmost vertex and I can continue my walk to the rightmost vertex. So in other words, the unitig in this graph corresponds to the read sequence from which the graph was built. So this is to illustrate that the value of k is important when we are building de Bruijn graphs, and one can ask what value should I use for solving the genome assembly for my particular data set. So typically the data sets won't be as simple as this. We will be working with millions of reads, and there we would like to pick a good value of k so that we can get as high quality genome assembly as possible. Now making this choice of or choosing an appropriate value of k is not easy, and I am illustrating this using this particular example. So you have again a genome sequence, and let us say you have a few reads sampled from this genome sequence. Now if I use k equals to 5, that is if I build a de Bruijn graph from 5 mers, then observe that the graph has tangles, that is it is not a chain like structure in which I can easily spell the genome sequence. So that is, in other words, there are vertices which have out degree more than 1, and I also see vertices which have in degree more than 1, right. So this will create ambiguity during genome reconstruction. Now what if I move to a larger k value, that is if I use a 6 mer. So in this particular example, if I use this k equals to 6, then it turns out that the graph becomes fragmented, and this is to illustrate that if you keep on increasing the k value, then ultimately remember that you also need k minus 1 suffix prefix overlap to join adjacent k mers, and for that you need to make sure that there is sufficient number of reads, that is you have sufficient coverage in your data set to avoid a break in the graph. So in this case, for example, there is a break from this vertex and there is a break between these two reads, because if you consider the 6 mer here, that is TGCAAG, and if you consider the 6 mer from here, that is CAAGGG, they do not have a 5 overlap, so that they do not have a suffix prefix overlap of length 5, and if they do not have overlap of that size, we will not be drawing an edge in the de Bruijn graph, and as a result this graph becomes fragmented. So a natural question is like, okay, with shorter k mer size the graph is tangled, and observe that this graph is tangled because of the repeat in the genome sequence. So there is a repeat in the genome sequence GCTG, due to which if you use a very short k mer size, then the graph will be tangled, and given the coverage we have for over this genome sequence, at 6 mer the graph is fragmented. So the question is what k mer value should we choose, because there is a clear trade off here. With shorter k mer the graph becomes tangled, and if you make the k mer size too big, then maybe the graph becomes fragmented. So the key idea in multiplex de Bruijn graph is to use multiple values of k simultaneously. That is, you want to benefit from the contiguity when you are working with shorter k mer size, and at longer k mer size you are able to resolve repeat sequence, but the graph can become fragmented. So in this case, so let us see how multiplex de Bruijn graphs resolves this issue. So now we are working with both de Bruijn graphs, that is you have a 5 mer de Bruijn graph and you have a 6 mer de Bruijn graph as well. The idea here is to compute unitics from both graphs. So that is you have unitics from these two graphs. So the two unitics will be, the first unitic in this case will be TGCAAG, the second unitic in this case is this second sequence. On the right hand side you have 3 unitics as highlighted now. So now you want to merge all these unitics and combine them. So when we are merging, we are ignoring shorter unitics which are part of longer unitics. So for example, let me use a different color now. So for example, if you notice this shorter unitic is part of a longer unitic here. So, in this case so this shorter unitic is part of the longer unitic here. So, in this case we will ignore this shorter unitic when we are merging, right. Similarly, in fact even if you see this unitic, so this unitic is part of the unitic here. So, again we will ignore this unitic when we are merging, and again we will ignore this unitic while when we are merging because of the same reason. So, ultimately we will pick two unitics based to avoid redundancy, and so these two unitics get selected and we will merge this unitic and have a merged unitic set. And from these unitics again we will build a De Bruijn graph using k equals to 6, and this time you will see that we are able to resolve the complete genome sequence. So, that is the genome sequence that we started with, we are able to get the same genome sequence when we build the De Bruijn graph. So, for example, now you build a 6-mer De Bruijn graph and you will observe that you will get a single chain like topology in which you will have a single unitic that spells the genome sequence. However, I want to mention that this idea is a heuristic, that is it is not guaranteed to work always. So, for example, I can from the same genome sequence I can sample the reads in a different manner. So, here I have sampled 4 reads from the same genome sequence, and now if you apply the same idea again, that is you build a 5-mer De Bruijn graph, you build a 6-mer De Bruijn graph, again you merge the unitics, and this time if you build a De Bruijn graph here, observe that you do not have a single unitic that spells the genome sequence. Again you have 2 unitics that are fragmented. So, in summary, this idea of using multiple k-mer sizes works sometimes and sometimes it does not work. So, it is a heuristic, and in practice what happens is genome assemblers move to a larger value of k only when they see that the new graph is simpler and remains contiguous. So, this is a heuristic that is selectively applied based on the data set we have, and the assemblers will continue to increase the value of k only up to a point where the new graph is simpler and remains contiguous. So, this is a simple sort of technique that is commonly used, and I wanted to cover this technique because some of the recent long read assemblers also use this concept of multiplex De Bruijn graphs. So, I hope the idea of multiplex De Bruijn graph is clear now. So, in De Bruijn graphs you are working with a single value of k, and the key difference in multiplex De Bruijn graph is that you can have multiple values of k. And this idea has been found to be useful in practice. So, even though there is no guarantee that multiplex De Bruijn graphs will give you better genome reconstruction, but in practice we see that the reconstructed genomes tend to be higher quality versus just working with a single k-mer value. Okay. So, that completes the discussion of multiplex De Bruijn graphs, and let us move to the third method for solving genome assembly, that is using overlap graphs. Okay. So, now what are overlap graphs? Well, overlap graphs work differently than De Bruijn graphs. So, again imagine that you have a genome sequence and you sample reads from the genome sequence. The overlap graph is defined as following. Here each read is a vertex in the graph and the edges represent suffix prefix overlaps between reads. That is, we are not breaking reads into k-mers now. So, there is no k parameter involved. Each read itself is a vertex in the graph and we are drawing directed edges based on the suffix prefix overlaps between pair of reads. So, in this example I am showing you a small overlap graph constructed from 5 reads R1, R2, R3, R4, R5. So, these 5 reads are being used in this example, and observe that as you can clearly see. So, if R1 is GTC GGCA, that is the read sample from the first few bases of the genome, then you have R2 read, and we draw edge from R1 to R2 because clearly there is suffix prefix overlap between R1 and R2. So, in this case you can clearly observe that there is suffix prefix overlap between R1 and R2, and that is why you have a directed edge from R1 to R2, and clearly you can see all other directed edges correspond to suffix prefix overlaps, right. So, again from R1 to R3 you have a overlap in this case. So, the overlap length is A. So, overlap length is 1 in this case. Similarly, you can see more examples. So, from R1 to R4 you have an overlap length of 2 and so on. So, whenever you see a suffix prefix overlap we draw a directed edge in this graph. So, now I hope the definition of overlap graphs is clear, right. So, let us see how we can use these overlap graphs in practice. Now, I want to remind you that overlap graphs are different from De Bruijn graphs. So, remember that in overlap graphs each read is a vertex, whereas in De Bruijn graphs each vertex is a k-mer observed in the reads. So, here all your vertices are k length words observed in the reads, whereas in overlap graphs reads themselves are the vertices. So, here R1 is a read, R2 is a read and so on. And also observe that in a De Bruijn graph you draw an edge when you have a overlap length of k minus 1. So, that is you are drawing an edge from GAC to ACC because there is a overlap length of k minus 1. Whereas in overlap graph we do not have such restriction. So, the overlap lengths are variable. So, in practice you can definitely have some minimum threshold, that is maybe you only want overlaps of at least 50 just to avoid false positives, right. So, just to avoid many false cases, false overlaps, you may put a minimum overlap threshold because you can always get a overlap length of 1 or 2 by chance, but with minimum length threshold after you apply minimum length threshold still the overlap lengths can be variable, right. So, there is no fixed value of an overlap length. So, these are two major differences between overlap graph and De Bruijn graph, and I should mention that there is no clear way of saying that okay one data structure is better than the other. Both have their own advantages and disadvantages, and we will see in the upcoming slides like what are the advantages and disadvantages of overlap graphs. I should also mention that the differences between these two data structures is not very well understood, and it is also a open research problem in some sense of how to relate these two data structures. Like for example, do we have any guarantees in terms of the output obtained from De Bruijn graph versus how will it relate to the output obtained from overlap graph. Okay. So, now I hope that it is clear how overlap graphs differ from De Bruijn graphs. Let us move on. Now, the definition that we have seen for overlap graphs, if we directly use that in practice, the graph can be very complex. So, for example, I am showing you a visualization of the graph, in which case I am drawing this graph from a very small number of simulated reads from human chromosome 20. In this visualization each colored rectangle indicates a read and the black curved lines indicate edges between the reads. So, in this case as you can see, this is not a easy to interpret graph. So, again we would like ideally a linear chain like structure, but this particular graph is very hard to interpret because we cannot see what walk we should use in this graph that would correspond to the actual genome sequence, right. So, inferring the correct walk associated with the genome sequence is hard. So, what do we do then? Well, one option is to simplify the graph. So, in practice once an overlap graph is built, we would use some techniques to simplify the graph and reduce redundancy in the graph. So, for example, as a first step what we can do is we can remove contained reads. If we assume that there are no sequencing errors, then I can call read A to be contained in read B if read A is a substring of read B. So, in this example read R3 is a substring of read R4. So, observe that. So, read R3 is ATC AC ATC, and you can see that it is a substring of read R4. And as it turns out, most of the contained reads in a dataset will be redundant, that is they add no value to the genome reconstruction problem. So, one way to simplify the graph is to remove contained reads because most of these contained reads will be redundant. So, in this case we can, for this example we can remove read R3 and we can obtain a simpler graph. Now, what next? What else can we do to simplify the graph? Well, observe that here in overlap graph we are considering all possible overlaps. So, not only you are considering overlap of R1 to R2, R2 to R3. So, in this case you are considering overlap of R1 to R2, but R2 to R3, but you are also considering overlap of R1 to R3 as well. So, there is redundancy in the edges as well. So, maybe we can avoid considering overlap between R1 and R3 because we can again spell the sequence from R1 to R2 and R2 to R3, right. So, we can jump from R1 to R2, R2 to R3, right. So, we do not have to jump from R1 to R3 directly. So, the next idea is to remove transitive edges. So, these are redundant edges because by removing transitive edges we ensure that the set of sequences spelled by the graph remains unchanged. That is, we are not losing any information when we remove transitive edges. Now, what are transitive edges? Well, transitive edges are redundant edges which will not impact the set of sequences spelled by the graph. Let me show you an example. So, observe that if you have this edge between R1 to R4. So, you have this edge between R1 to R4. Now, if you spell the genome sequence by going from R1 to R4, you can spell the same genome sequence by moving from R1 to R2 and then R1 to R2 and then R4. So, both of these paths will lead to the same genome sequence being spelled, and you can verify this. So, for example, in this case I am showing you this sequence spelled by this first path in light blue color. So, in this case the sequence spelled by R1 R4 path will be GTC GG CA, and then ignoring the overlap here it would be TCA CA T CTG. So, this would be the sequence spelled by path R1 R4. And if you consider path R1 R2 R4, that is the longer path, then again the sequence being spelled remains same, right. So, it is a transitive edge, that is you can represent the same information from moving from R1 to R2 to R4, as well as you can spell the same sequence moving from R1 to R4. So, again in this case the sequence spelled is this followed by TC followed by ACA TCG TG, and you can verify that this sequence matches with the previous sequence. So, in this case what we can say is that the edge from vertex R1 to vertex R4 is redundant and we can get rid of this edge, right. So, the relationship between R1 to R2 and R2 to R4 is sufficient for now, and we can simplify the graph by removing this edge. By doing so we guarantee that the set of sequences spelled by the graph remains unchanged. And it is easy to detect transitive edges, because as you can imagine all we have to do is somewhat, this is very similar to triangle finding, in which you locate the triangles in the graph and then you check the sequences spelled by two paths, and if they are same then you remove the third edge. Again, so if we continue further we will again see that there is one more transitive edge in this example. So, from R2 to R4 and R4 to R5 it spells the same path as R2 to R5. So, again we can simplify further and remove one more edge to get a simpler graph. So, in this process what we end up simplifying the graph significantly in practice. So, we were working on this toy example for now, but in practice as well these techniques work really well in obtaining a much simpler graph. So, on the same example that I was showing you before, where we had a complex graph topology. So, in this case this was complex to work with. After you remove contained reads you get a simpler graph, and after you remove transitive edges, for this particular example you get a simple chain like structure in which we can easily spell the genome sequence from left to right. And this simplified structure after we remove, so the graph obtained after removing contained reads as well as transitive edges is also referred to as string graph. Right. So, in this simplification process in theory we know that the transitive edges is a safe technique, that is the edges that we are going to remove are absolutely redundant. However, when we are removing contained reads we know that most of these contained reads will be redundant, but there is no guarantee here, that is sometimes we may also end up losing useful vertices which would be needed to spell the actual genome sequence. So, in this case this is a safe technique, that is we do not lose any information, but this is not necessarily safe. In occasionally this can lead to creating mistakes as well. So, let me show you an example of why this is not safe, like why occasionally we can also make errors when we are removing contained reads. So, this is an example to illustrate where removal of contained reads can occasionally create problem as well. So, this particularly happens when you have repeats in the genome. So, here observe that in this genome sequence there is a repetitive region. So, there is a sequence that is repeated twice. Now, in green color I am showing you the reads sampled from this genome sequence. Observe that read 2 is contained in read 1 as well as read 3 is contained in read 6 because of the repetitive structure of the genome. So, because of the repetitive structure you can see that read 3 will be a substring of read R6, and in our technique because we are observing only the reads themselves, we do not have access to the genome sequence. When we remove all the contained reads, what it turns out is that when you remove the contained reads, so in this case you will remove contained read 2 and you will remove read 3. And once you remove read 2 and read 3, observe that the graph becomes fragmented, that is, you have lost the way to connect read 1 to read 4. So, there is no edge between read 1 to read 4 anymore, because you have removed all the contained reads. Now, as I said, most of the contained reads in practice will be redundant, but occasionally some of the contained reads can be useful, and unfortunately it is an open problem of how to detect those useful reads. Like, there is no clear methodology in which we can clearly say that these contained reads have to be used for preventing this issue. So, this is one of the open problems for overlap graphs, like how do we address this limitation, because we cannot afford to keep all the contained reads. If we keep all the contained reads, then we go back to the complex graph which cannot be used, which is not useful in practice. So, occasionally this contained read removal can also disconnect the graph, but this happens occasionally. So, most of the contained reads in practice will be redundant. Okay. So, yeah, so basically in the overlap graph data structure, basically we assemble the graph by simplifying the graph using the two techniques, and once we have a simplified graph, we would spell the genome sequences based on the paths observed in the graph. So far we have seen three most popular algorithmic paradigms for solving genome assembly problem, right. So, we went into de Bruijn graphs into significantly more details, and then I gave you an overview of how multiplex de Bruijn graphs and overlap graphs work in practice. Now, this covers the algorithms that are used in practice in the modern genome assemblers. The last remark I want to make in this lecture is the important role of sequencing technologies. So, sequencing technologies play a significant role in shaping the field of genome assembly as well. Remember that we need high quality input for solving the genome assembly problem, because when we are solving this jigsaw puzzle, the quality of your pieces matter. Like, do you have all the pieces, are your pieces long enough, and are the pieces broken, or are the pieces very well intact. So, in the context of sequencing reads, we would ideally want sufficient coverage so that the entire genome is covered by reads and you have enough overlap between adjacent reads. Read lengths also play a role, because if you have short read lengths which do not bridge repeats, then again you will end up having a graph which is tangled, which will lead to ambiguity during genome reconstruction. So, if you have long reads which span repeats, this ambiguity can be resolved and your graph will be much simpler. The third point is read quality, that is, if you have significant errors in your reads, then finding suffix prefix overlaps can become challenging. So, again the quality of reads themselves also matters, that is, both length as well as error rate in these reads plays an important role. So, ideally you would want as long reads as possible and you would want as accurate reads as possible, that is, error rate should be as low as possible. Okay. So, with that in mind, let me give you one example of how sequencing technologies has shaped the problem of genome assembly and how it has impacted the quality of assembly outputs. So, post 2010 we have new technology which is known as long read sequencing technology. The unique aspect of this technology is that the length of the reads that we get is much longer compared to the previous short read sequencing technology. So, 2 decades ago we would assemble a genome by using small reads which were only, let us say, 150 base pair, long, whereas now you have reads of length more than 10,000 bases long. So again, in the context of genome assembly, and if you remember the analogy with jigsaw puzzle, now we can say that we are working with longer pieces, and the difficulty level of solving the jigsaw puzzle has reduced in some sense, because now you have access to longer pieces and solving the jigsaw puzzle will be much simpler when you have long reads, right. So here is how these long reads have changed the quality of genome assembly output. So I am showing you the the visualization of genome assembly of a human genome. On the left you see a visualization of the assembly of from 2001, and on the right you see the assembly from 2019. So each vertical segment in this figure shows you a chromosome. So that is chromosome 1, chromosome 2 and so on. These light gray and black strips indicate each assembled sequence. That is, whenever you are oscillating between gray and black, it indicates a break in the assembly. And remember that breaks can happen due to repeats. So when your reads are not spanning the repetitive regions, then you will have a break in the genome assembly. So frequent these short gray switching of gray and black colors is indicating frequent breaks in the genome assembly. So each contiguous color represents a single sequence, and next sequence is represented by alternate color. What you can see is that the contiguous blocks, that is contiguous gray and black colors, are much longer on the right hand side. That is, you have significantly contiguous assemblies in 2019 compared to 2001. So here you have frequent breaks in assembly, because we were working with short sequences, and here you have contiguous assemblies. That is, they are almost the contiguity or the length of these sequences is in the order of the length of the chromosomes themselves. And here I am showing you this picture to just show you an impact of how sequencing technologies can dramatically change the assembly output as well. So this particular assembly was computed using long read technology, which I just talked about in the previous slide. And you can see that how when you have longer reads, you can reconstruct genomes with much better quality, because they help you bridge the repeats in the genome sequence. So when you are able to bridge the repeats, you have much simpler graphs, and you can reconstruct much longer unitics and much longer contigs when you are trying to spell the genome sequence from these graphs. So this is one example, and these sequencing technologies continue to evolve rapidly. So for example, every month we see some news article coming up that tells you about what new has happened in the space of sequencing technologies. Like sometimes you will see improvements in cost, improvements in accuracy, improvements in throughput and so on. So again, these sequencing technologies also evolve rapidly, and they also play an important role in shaping the field of genome assembly. Now as these sequencing technologies continue to evolve rapidly, they also inspire new research opportunities. So as an example, from 2020 onwards, we saw new advancements in technologies which allowed us to sequence long reads at much better accuracy than before. So looking at two examples, you can see that the accuracy of reads improved to above 99%, and the average length exceeded from 10 kilobase pair. So these led to this led to thinking of new challenging problems. For example, assembly of challenging diploid, polyploid genomes, cancer genomes, because now you have much better quality of data to work with. And that is why genome assembly also remains an active research topic, because of these frequent updates to sequencing technologies as well. So, here I want to give you 2 review articles as well. So, if you want to learn more about the context of genome assembly, like for example details of these data structures and how they have evolved in the past, you can take a look at these 2 review articles. They are excellent material to learn more about genome assembly problem. So, concluding this lecture, we have looked at 3 types of assembly algorithms. In the last lecture we covered de Bruijn graphs. In this lecture we covered multiplex de Bruijn graphs as well as overlap graphs. I should mention that all these 3 algorithms are powerful and very effective. They are used in modern genome assemblers. However, all these algorithms also have limitations, which means this is an active research topic as well. We also looked at the role of sequencing technologies, like how the evolution of sequencing technologies has impacted the quality of assembled genomes. So, with that we will close this lecture, and this lecture also finishes the module 5 of genome assembly using graph algorithms. From next lecture onwards we will start a new module. Thank you.